Here we go. We're going to look at 6.4. It's the properties of logarithms. They're really important. They're not exactly intuitive, but I'm going to show you what they are and practice with them, and you'll have them down. It'll be great. And so here we go. Paper view and our notes 6.4. The base. So all the usual restrictions are going to apply as we go over these properties. On all of these down here, I have the base being A. Remember what we said about the base. We said the base had to be greater than 0 and not equal to 1. And so this will be true as long as our base is greater than 0 and not equal to 1. Now, one thing that you might have noticed about logarithm, but you might not have noticed about logarithm yet too, is the input has to be greater than 0. And so that's something that's going to become apparent to us in this lesson here for certain if we didn't already kind of start to think that a little bit. So M and N are the inputs that we're going to be using. The inputs into the logarithm M and N right here, and they have to be greater than 0. And P and K are going to be exponents that are running around. And K is, there's a K somewhere right there. It is K. And they say they can be any real number. And we're going to try a few with our calculator. We're going to let our calculator do a little bit of, oh yeah, that's true. And what do you think it would be? And check it out on your calculator. So it says log base A of 1. And so I'm wanting to, I got both my calculators going. So I'm going to hit the log. Now, A, just pick anything that's appropriate. So it has to be greater than 0 and not equal to 1, because all we're going to do is we're going to do this multiple times and see if we can see a pattern. And then make a, because my calculator won't do it with A. So I'm going to do base 10. I'm going to put 1. And when I do that, I get 0. Okay. And on this calculator here, I'm going to do the logarithm. And I'm going to put base 2. And I'm going to put 1. And I get 0. I'm going to go back to this calculator, and where I had base 10, this calculator is actually a little bigger, brighter, huh? And where I had base 10, I'm going to put base 109, just because I accidentally pushed 9, and I get 0. And on this one, I'm going to come in here, and I'm going to change that to 57, and I get 0. And I'm going to come over here, and I'm going to change that 109. I'm going to change that 109 to a 2.589. And so a big decimal I got there, and I still get 0. Now, I didn't choose anything I wasn't allowed to choose. If I chose something I wasn't allowed to choose, like I chose a negative, then what I'm going to get is math error. So if I chose -2, I'm going to get math error, because you're not allowed to choose that. But as long as I was choosing things that I was allowed to choose, do you guys notice that I got 0? And so every single time. And this is not a proof, but does it make you feel like the answer is for this, for any value of A, doesn't it make you feel like it is 0? Now, that's a 0 that almost looks like it has a tail, but 0. And so now I can show you by writing it in an exponential form and convince you that, oh yeah, that's what it would be. Because we're not real familiar with logarithmic form. You get more familiar with it as you work with it, and particularly if you work with it by hand, you'll get more familiar with it. But we're more familiar with exponential form. So the base, if I'm going to write this in exponential form, I start off with the base, which is A. So this is now, I'm going to write this in EXP, exponential form. And then I say to myself, well, log needs an exponent, right? And so put your finger over the log, because log equals the exponent, which is 0. And that equals the only number there, 1. And that certainly is true for every value of A. We have been told, right? That was one of our properties that we did. Just a second, someone's texting me, and I'm going to tell them, I'm going to text him. I tell them I would call them in here in a minute. Okay, let's try this one. I hope that you already started. The base and the input have to be the same. And so we're trying it on our different calculators. So on this calculator, I already had the base in there of 2.589. So I'm going to delete out the 1 and put in 2.589, and I get 1. And so over here, I had base 2, and so I'm going to change this to be base, I'm going to delete that out, and I'm going to have log base 2 of 2, and I get 1. And I want you to try a few as well. So you be naming some that are appropriate. So it's okay to pick 23 as my base. And then my input, I want it to be the same, 23. And I get 1. Do you think that I always, if my base on my logarithm and my input are the same, do you think I always get 1? And the answer is, as long as you've picked something appropriate for the input and something appropriate for the base, then you will. So not everything's appropriate. Not okay to choose a negative for the input. Not okay to choose a negative for the base. It's not okay to choose 1 for the. So right here, it's not okay to choose 1 for the base. So as long as I choose something that's appropriate, I do get 1. Now, I want to convince you that it's true by writing it in exponential notation. And you'll be like, oh, yeah, it is true. Definitely. The base is A. It needs an exponent. And remember, log equals the exponent, right? So put your finger over the log, and that equals the exponent, 1. And then the only thing left is the input A. So equals A, and A to the 1 does equal A. So you can totally convince yourself that, hey, this would be true. The next one here is a little bit different, but I don't think I'll take very long in convincing you that it's true just by trying a few numbers. And so, and if you wanted to go and look in your book, they show you that this is true using exponential form, just like I just have done. And so you can definitely do that if you like. So this one says log base A of x is the exponent. Remember, log is an exponent, to which A must be raised in order to get x. And so this thing right there, that log right there, is an exponent. And so let's give a try to a few. You notice we have a base of A, and that is in exponential form. So I'm going to just choose any appropriate value for A, and we're going to trade it out. So I'm choosing 2. And then I want to raise that 2. And then it says log of the same base. So log base A. So that is important. I almost feel like I need to zoom that in. I don't know how to zoom in. That zoomed out. And then focus. Are you going to focus, baby? Really bad idea. That's a little bit closer so that we can see it because it's such a little A. Okay, log base, log base 2. And so, and I'm going to put in any value for x. So 9, I'll just choose arbitrarily, and I get 9. And now I'm going to change those because it's saying this is an arbitrary value A as long as appropriate, and log base of that same A as long as it's appropriate. And so if you guys are saying make it into 20, then great, that's what I'm going to do. And I got 9 again. Now, if I came in here and I changed that input right there to say 56, what do you predict I'm going to get? And so when I hit equals, I get 56. I hope you're playing around with it a little bit and kind of seeing how things would go. And so I'm going to change this to be, I don't know, 2.5. And I'm going to change this right here to be 2.5. And I got 56 there, and I get back 56. If I change it to 156, what do you think I'll get as it's going to pop out 156, right? So, so definitely, so what would this be when I'm leaving it as x? And it's like this and that are inverses of one another. and they undo one another and just give me the input x is what they give me. Yeah, this is x is what it's equal to. Now, if you wanted to try and see if it would work out using to make sure that it seems true, like these seem true using exponential notation, we certainly could. So I'm going to go, using logarithm notation. This is in exponential notation. It has a log in it as well. But this right here is just the exponent. So where I start off with when I'm going into log notation is what I want to go into to convince you of this, is I start off with the exponent. And so that's what I start off with, which the exponent is log a of x. And then I chant, an exponent equals a log, right? And so we just got the exponent right here, and that equals a log. So I write the word log. And then I tell myself a log needs a base, and the base is a. And the log needs an input, and the input is x. And you notice that's certainly true, right? Log base a of x equals log base a of x. So this is in log form. So it's certainly true. And we tried it a few times on our calculator to convince ourselves that, hey, this would be true. So those were those ones right there. Then we're going to look here at the product rule and the power rule and the quotient rule. And then this is another inverse rule is what it is. And I'm going to have a harder time convincing you, because it'll be a lot to keep straight, that it's true with some numbers. But you certainly can, if you like, to do a few numbers, you can. And maybe I'll even show you with a few nice numbers. So I am writing down what it is equal to, but don't say to yourself, where did she get that from? I got it from the book, and I have memorized it. So that's how I know what it is equal to. It's log base a of m plus log base a of n is what it is equal to. Now, if we wanted to try it with a few numbers, just so that you could be convinced that, hey, it's true, I'm going to flip my paper over and or get a new piece of paper. And I'm just only going to do it just one set of numbers. Log base a of m times n. And I just told you that was equal to log base a of m plus log base a of n. And that means this should be true for every value of appropriate value of a and appropriate value of m times m and n. And so I'm just going to make up appropriate values. They all have to be positive. So log base and name me a value. I wish I had a die. I would roll it. 3. Okay. And then I'm just going to pick some values that are appropriate. 4 times 5 equals log base 3 of 4 plus log base 3 of 5. And then I'm going to show you with these two calculators that these are equal to one another. So right here on this one calculator, I'm going to put this one in. And yeah, 4 times 5 is 20. But I'm going to hit the log key. I'm going to put 3. And I'm going to go in here and I'm going to put 4 times 5. And that's 20. And I get 2.7268330 whatever. And on this calculator here, I'm going to put those two things is what I'm going to put. So I'm going to hit my log key. And I'm going to put base 3 of 4 there. And plus. And then log. This is not a proof. This is just showing that, hey, look, it's true. Right? 5. You probably have forgotten the number. But here they both are together. They're equal to one another. Right? Not almost equal to each other, exactly equal to each other. And if they didn't turn out to be exactly equal to each other, at some point I would be telling you it was a calculator making a mistake, because they are equal to one another. Okay, so we did a lovely job on just kind of looking at an example there on that. And then the quotient rule. Now, if a product was addition, and let me remind you of the product rule for exponents. Remember, these are the inverses of exponents. Remember, you add the exponents. Do you guys remember that? logs are exponents. Here we are adding the logs. And so do you remember when we had a quotient, do you remember that you subtracted the exponents, and logs are exponents? So this is going to be log base A of m minus log base A of n. Hey, can I call you back in just a few seconds? I'm making a video for my class. I'm doing really well, and I'll call you back in just a few minutes. Okay, bye-bye. That's my daddy. And so I have to check on him always. Love that guy, love that guy, love that guy. Got two daddies, and I love them both to death. That was daddy number 2. Okay, I wouldn't be surprised if daddy number 1 didn't call me here in a minute. Okay, so now the P is out here, and they say that P can be any real number, and this is the power rule. And I don't know if you remember the power rule, but it said that what you did with your with the exponents, remember log as an exponent, is you multiplied them together. So P is an exponent here, and log is an exponent, and so we're going to do that same thing. P times log base A of m. And I know, weirdest property on the earth. Absolutely the weirdest property on the earth. If you want to try it with some numbers, I really, really, really encourage you to do that. So I'm going to try it just over here with some numbers. Log base 6, just making up a number, right? And I'm going to put right here 4 raised to the 3rd, okay? And according to this property, that this is equal to 3 times log base 6 of 4. So on this calculator right here, I'm going to put log 6. I just made those numbers up. So you're like, where did those numbers come from? I just made them up so that we could just see that, hey, yeah, equal, right? So there I have put this side, I'm getting it, this calculator, so that I have put this side in, right? There's always parentheses around your input. I hit equals, I get 2.32, coincidentally. And then here, I'm going to try it on this calculator, 3 times log 6, 4, right there. And I get the same thing, exactly the same. And I didn't expect to get something different. They're equal to one another. And those properties of logarithms come from the properties that we had with the exponential. I just want to show you with your calculator so that you can be convinced that it's true. And I hope that you play around with some yourself. Toy with it and just see. People didn't have calculators. You know, you're lucky to be able to toy around with it with a calculator and say to yourself, hey, and be convinced that, hey, this is definitely true. Okay, if you were just guessing, this is log base A of A raised to the K. If you were just guessing, what would you think that would say that this is equal to? And I'm encouraging, definitely, so log, you name the base. If I had dice, I would say roll the dice, right? And come up with a value, 10, I'm saying. And then this is saying 10 to the K. And 10 raised to the K, we're going to say K is 2. And I get 2. So is that what you guessed? That it was exactly equal to K? Now, it makes sense, right? Because if you use the power rule, all these rules go together. If you use the power rule, this would say that K, which is the exponent, just like this P was the exponent, goes down in front and they multiply with one another. K times log base A of A. And then do you remember what log base A of A was equal to? Was equal to 1. So this is K times 1, which is K. There's a lot of different ways of looking at it. And so those are those properties. Go watch videos on them and go look at how they prove them. I didn't prove them. I explored with them a little bit, and you can explore with them a little bit more. Now, what they're asking us to do is practice with them. And what they're wanting us to do to practice with them is they're wanting us, I think I can go a little bit closer. Without going blurry. What they're wanting us to do here is they're wanting us to expand as much as possible And I say write the word log as much as possible. And the reason they're wanting you to do that is just to get some practice on expanding and collapsing. Typically, what we want to do is collapse. But how do you learn to collapse? By practicing your expanding as well. Okay, so this is about as collapsed as you can get. And so if I wanted to expand this, I notice that that's a product between 3 and A and B. And what did it say to do with the product? It said they would all have the same base log and you add them, right? And so you can break this apart into log base T of 3 plus log base T of A plus log base T of B. And now I've written log as many times as I can write log with this. And I think they say, some books say as a single logarithm. And so now I have a single logarithm without a product. So I expanded it as far as possible. Okay, so we're going to try this one, example 2. It's got, this is the input right here. That whole thing is the input, that division. And remember what you do when you have a division. When you have a quotient, a division, you subtract them. So that's the first thing I'm going to do. So this is log base B, and I'm going to do the numerator, w squared x minus log base B of the denominator, which was y to the third z. And then remember, we're trying to expand as far as possible. So this is a product, so I can expand it further. And so when I expand this further, this is log base B of w squared plus log base B of x. And the same I can do here. Now, when I go to this is right now a single logarithm. It's a monomial. And when I expand this to be two things, this negative has to distribute. So I'm going to put parentheses right like this so that when I expand it, you'll see that it's distribute, right? So parentheses are always implied. And because one thing, that one logarithm is going to become 2 logarithms, that's definitely a time when you want to put in parentheses. Now, why did I not do it here? Because it had a plus following it. And if you distribute a plus, it doesn't change things. So this is going to be log base B of y to the third plus log base B of z. And then that negative can distribute. And so what the heck, I'll distribute that negative. And then there's one more thing I can do. And they're having me practice. So I'm distributing the negative. So a negative times a positive times a positive, negative here. If you're noticing that all the ones that were in the numerator have positive before the logarithm, the w squared and the x, and all the ones that are in the denominator have negative before the logarithm, you're right. And that's a shortcut you could take, noticing that. Now, this exponent 2 right here, do you remember where I could write that exponent 2? It was really weird. But the exponent right here, the exponent, I used to say when I first started teaching that it scooches down. I don't know why I said that, but that's what I used to say, and that word just came to me just now. And so this 2 becomes the exponent. So 2, this 2, that's an exponent, multiplies with the log, that's an exponent, because that's the product rule. Power rule, log base B of W. This doesn't have an exponent, so it's all good. Its exponent is 1. This one has an exponent, so do you remember where you can move the exponent? And this one doesn't have an exponent. So this is what they were wanting from me, and expanding it as far as I possibly could. And so they're wanting me to pick it apart. Really, most of the time, what you're wanting to do is push it together, is what you're wanting to do most of the time. And so the next things that they're going to do is they're going to give me something like this, and they're going to ask me to try to push it back together to that. And so we're going to work on that. So that's usually what you're wanting to do. I said you try it. This is an expand as much as possible. So if you want to, pause the video and give it a try, and I'll assume that that's what you did. Okay, so you're back, and you're going to compare and see if you got the same answer. And so this is raised to the fourth. So this is log base b, and this is raised to the, I said fourth, but I didn't mean fourth. What did I really mean? I want to write it down a little bit. I wish I would have gave myself more room here for writing a little bit bigger. Log base b. Yeah, raised to the 1/4. That's what I said, fourth, but I meant 1/4. So this is, I'm having to write on the line, which is really bothering the heck out of me. My OCD problems are kicking in, and I'm saying, you know, oh, I don't like that. I don't like that. Okay, so I have that. So what could I do with the 1/4 that I just put here? It was over there. So if you're saying that, hey, you could use that rule that said that this is a power and that you multiply the exponents when you have a power like that, the power rule, that you're right. And remember, log is an exponent. So we're going to multiply the 1/4. It's really weird. It takes getting used to. You're right. There's another way that you could have done the problem. And if you did the problem a different way than what I'm doing right now, know that there's another way. So wait and just watch how I do it, and then see if that if we get the same answer, because I think we're going to get the same answer. Now we can blow this apart, and right, and so this is going to be, and I'm going to write it down here, 1/4. And then I'm going to blow this thing apart. And the 1/4 is on the outside, right? And because it's 1/4 goes with all of it. And so this is going to be log base b of x to the 8, y to the 12th, adding, subtracting these, right? Okay. So log base b, we're supposed to expand as far as possible, x to the 8, plus log base b of y to the 12th, minus log base b of b to the 3rd, and minus, because it's in the denominator, log base b of z to the 5th. And it said expand as far as you possibly can. Try to use all those rules of logarithm, and we're trying to blow it apart as far as we possibly can. And so now all of those exponents, the 8, the 12, the 3, could all go down in front. Eight log base b of x plus 12 log base b of y minus 3 log base b of b minus 5 log base b of z. So we did a lovely job on that. Other than, do you guys see one of those ones that will simplify log base b of b is equal to 1? Using my property of logarithm, this is equal to 1. Other than that, this could be a good answer. And it also would be a good answer to multiply the 1/4 in. And so let me write it this way, and we'll call it one good answer of expanding it as far as possible. 8 log base b of x plus 12 log base b of y minus 3, because this is equal to 1. And I'm going to run out of room, so minus 5 log base b of z. I had to squish it in there. Okay. Also, you could distribute the 1/4. So this is a good answer. And you could distribute the 1/4. 1/4 of 8 is 2. So 2 log base b of x. 1/4 times 12 is 3. 3 log base b of y. 1/4 times negative 3 is negative 3/4. And 1/4 times negative 5 is negative 5/4. Log base b of z. That's also a good answer. So all of those are good. Now they're wanting us to practice making them. So you probably got a similar answer, maybe. Maybe you didn't. That was a really hard one. And so what does it take to be able to do these and to practice with them? They're really odd. It takes a lot of practice. But logarithms come up in a lot of things. And so if you're wanting to go into any science, they come up all over the place. And they're doable. They're just really weird at first. And so don't get discouraged, get encouraged that you can do it. And so this, they're wanting me to express the equivalent expression as a single logarithm and simplify. So they're wanting me to collapse it down to one logarithm. So I'm going to be using those log properties. And I have this log property. I'll get my log properties over here. That says if you're adding two things with the same base, that you can multiply their input and put them as one logarithm. So that's what I'm going to be using here, is I'm adding these both. They have the same base. If they didn't have the same base, I wouldn't be able to do this. And so it says that what you can do is write them with one base, and you multiply their input, which was 5 times 9, which is 45. So this is log base b of 45. And so this and this are equivalent to one another. They're wanting me to do that again on example 5. And then I have a U-try-it on example 6. And man, the U-try-its are always harder than the ones I got to do. But the good news is that you do it and I'm going to do it as well. So I'm not you-trying it and then you just have to do it on your own. My family is going crazy. Everybody's calling me. Everybody's texting me. They say, it's 7:19 at night. You're certainly not in your classroom. They would be wrong. Here I am. And so the exponent right here is 3. And, this can be moved to be the exponent, right? Because you can't use any of these properties to put it together as one logarithm unless it is just a single logarithm in the front. And so you notice that? No number here in the front. You can't have a number. And so if you have a number in the front, see how I have the number here, p in the front? You have to move it to the exponent. Then you can use these other rules. I know, kind of weird, huh? That's the first time we've said that, hey, you can't have, it has to be perfect in order to use it. And yeah, it does. So this 3 right here can be moved to the exponent. So this would be log base c of p to the third. And then this 1/2 could be moved to the exponent. So then this would be plus log base c of t to the 1/2. Minus, and this doesn't have a coefficient, so minus log base c of 7. So I've done the first thing, which is get it so they're all just log. So if they had a number, so if it was 3 log, then you move that 3 to the exponent so that you can just have log, log, log. So now I have log, log, log. And I'm going to put it together. When it's plus, you multiply. And when it's minus, do you guys remember what you do? When it's minus, you divide, is what you do. So the ones that are going to be in the top and are going to be multiplied are the p to the third and the t to the 1/2. So this is log base c, one time writing the log. And this is going to be, I'm going to put this all in here. In the top, I'm going to have p to the third and times t to the 1/2. I don't have to put the time symbol. And because it's minus in the denominator, I'm going to have 7. And then that's done. Now, when I look in the back of the book, I might notice that they write t to the 1/2 as the square root of t. Because do you guys remember that that was true? That t to the 1/2 was equal to the square root of t when we did exponents I don't know if you remember that. It's been a while ago when we did fractional exponents. And so I'm pretty sure that that's probably how they written it in the back of the book. So that's the next thing that I'm gonna do. There we have it. If those reduced, you would reduce them. Like if the 7 and the p to the third reduced with one another, it doesn't, but if it did, you would reduce it. Okay, now it's a you try it. And so pause the video if you want to give it a try. And so I'll assume that you did pause the video and tried it yourself. And it's probably more important to give things a whirl on your own than it is to watch someone else do them. Definitely, that's true with mathematics. Now, this one's a little, I got that minus. And so that means that if I want to, and I don't have any coefficients, so that means if I wanted to put it together with one logarithm, it would be a division. And I would be dividing 2x plus 10 and x squared minus 25. And you should reduce it if it reduced. So just like p to the third and 7 didn't reduce, right now it doesn't look like 2x plus 10 and x squared minus 25 would reduce with one another. But how you reduce binomial as opposed to monomial is you factor it. So I should be looking at how does this factor? And because it's a binomial, I'm saying to myself, and I'm trying to factor it, right? Factoring. And you're like, oh man, we did so much factoring. I thought that went away. Really? There's going to be more factoring right now? Greatest common factor. Yeah, there's going to be more factoring right now. And a difference of squares and a cube, right? And so that's how we factor when we have a binomial. We ask ourselves, does it have a greatest common factor? Is it a difference of squares? And you notice the numerator has a greatest common factor. And the denominator is a difference of squares. And then if anything in the top is exactly the same as anything in the bottom, it would reduce. So bye-bye to the x plus 5s. X plus 5 divided by x plus 5 is 1. So I have log base a of, and then I have 2 divided by x minus 5. And then I'm done. And that's all I can do. And they asked me to write it in one logarithm and simplify it. And so I did. These take practice. You'll get good at them. You'll be very good at them. So now they're going to show me how to solve some problems with logarithm. And there's more than one way of doing it. And it kind of depends on what you have, on what you do. Just like quadratics, we have three different methods of solving a quadratic, right? And some quadratics will be solved by all three of them. Some will be solved by always the quadratic formula, right? And so one thing, if you have problems that involve logarithms and you're trying to solve them, and if you have logarithm on both sides, this is what this is saying, and it's the same base, then you can equate the inputs. And so you have to simplify this down to one logarithm on this side, and I already have one logarithm on that side. Then I can get rid of the log part, log base 4, because it'd be all the same, and I can equate the inputs, is what that's called. So the input is x and the input is y. They're saying if you have exactly the same as far as the log a and the log a, that you can equate the inputs, y equals x. So that's kind of the story. There would only be equal if the inputs were equal. So my idea is to write this as a single logarithm using my properties of logarithm. And they have to have the same base, which they do. It's 4, so that's good. If they didn't have the same base, they wouldn't be able to do that. Then the next thing is that if you have add between the logarithms, you can't have any coefficients. So I don't have coefficients. That's example 7, right? No coefficient there other than 1. No coefficient there. So you can't have coefficients. And if it's add, you multiply the logarithms together. You multiply the inputs together. So this is log base 4. And I'm going to multiply those inputs. X plus 2, x minus 7 equals. And I just put brackets around it to show that's one input to that logarithm. That's the new input. Equals log base 4 of 10. And so now they're both sides are log base 4. And so you can equate the insides. You can equate the inputs, which is x plus 2, x minus 7 equals 10. And then that is something that we solved a while back. And unfortunately, you have to FOIL it together and get 0 on one side and hope you can factor it or use the quadratic formula. Because it's not helpful to solve something that's like this if it doesn't have 0 on one side and I have 10 on one side. So unfortunately, I have to FOIL this together. And so get ahead of me and FOIL it together yourself. So I get x squared minus 7x plus 2x minus 14 equals 10. So I get x squared minus 5x, and then I'm going to take away 10 because I want 0 on one side, minus 24 equals 0. And then now I have to use the quadratic formula, or I can factor it if it factors. I can't use the square root property because it has the middle term. And so I probably, 24, let me think, 3 times 8, right? Makes 24, and that kind of gives 5. So I can factor this. I feel happy that I can factor it. So this is x minus 8, x plus 3 equals 0. So I get x is 8 and x is negative 3 when I set those equal to 0 and solve them. So those are my two answers. But remember, there's a lot of things about logarithms that are not allowed. So you have to always check your answer. Always check. So the input and the base and the input to a logarithm have to be greater than 0. Either one of those. So it's not, whatever one you have, the input or the base have to be greater than 0. There are 3 pieces of a logarithm, and one piece is allowed to be negative, and the other 2 pieces are positive. So when I go back up here to check in the original, log base 4, and if I'm checking x equals 8, check them one at a time here, then this would be log base 4 of 8 plus 2 plus log base 4 of 8 minus 7 equals log base 4 of 10. And I'm just going to check with my calculator that it's true. So I've got my dueling calculators. And so I'm going to check this side over here with the 991, log base 4 of 8 plus 2, which is 10. And I'm okay with adding that together and saying that's 10. But I just decided to put it in the calculator without adding it. But that would be okay to do. And then 8 take away 7, and I'm okay to say that's 1. So when I hit equals, I get 1.6609. It didn't give me error. Now, it wouldn't give me error unless my input was negative. My base is 4. And so unless I had a negative in my input, and I had 10 and I had 1, so I should be okay. And then on the other side, I have log base 4 of 10. And I'm wondering, are these equal to one another? And they are. So yay. That means 8 was a good answer. So yay, put a smiley face on it. Now I want to check x equals negative 3. So when I check it, back in the original, log base 4 of negative 3 plus 2 plus log base 4 of negative 3 minus 7 equals log base 4 of 10. And here's what the problem is that's negative 1, and that's not allowed. So when I put that in my calculator, it's going to give me error. That's what it's going to say. So when I put in here negative 3 plus 2, because that's equal to negative 1, my calculator is going to say error. Even if I put the rest of it in, plus log base 4 of, well, that's negative as well. Negative 3 minus 7, and it's going to say error. It doesn't do it because the input is not allowed to be negative. And right here, it was negative 1. And here, it was negative 10. That's not allowed. So what does that tell us about x is equal to negative 3? That means that is not a good answer. So I would cross it out. And the only answer I have is the one that checked, which was x equals 8. And I wouldn't mention anything about x equals negative 3. If the book says it's extraneous, they're saying to you, don't be tricked by it. It's not a solution, is what they're saying. Okay, so that's one method of solving logarithm for, and this is when you have logs on both sides. Now we're going to look at some more thoughts on solving problems that have logarithms. What if it doesn't have log on both sides? Then how can you solve it? Okay, some thoughts for solving problems where the variable is in the input of the logarithm. Isolate the logarithm. Put it in the form log base b of x equals k. Here x is the variable. This may involve some or all of the properties of log that we learned a bit ago, just one page ago. From here, write it in exponential form and solve normally for x. And so, and that's kind of where they started us. Yesterday, they had us solving problems that look like that. And they said, all you have to do is write it in exponential form. And now they're going to give me problems and want me to boil it down to that and then do the same thing. So that's kind of what we're going to do. And then you must check your answer at the end. The input to the log must be positive, not 0 and not negative. Also, the base of the log should be positive and not equal to 1. And so, but the log has 3 pieces, right? Let's name all the pieces on our logarithm. So right here, logs have 3 pieces in this form. That piece right there is called the base, and is typically either called B or A, either one. This part right there is called the input. Some people call it the argument. And then equals, and then K on the other side, over here. This is the exponent, because log equals an exponent. And so here's the story. The base has to be bigger than 0 and not equal to 1. The input has to be bigger than 0. And the exponent can be whatever the heck it wants. So that's the story on that. So we have just 2 problems, and then I'll relieve my family of all of their questions. So I notice I don't have logarithm on both sides. Do you notice this side has the 2 logarithms on it and the other side has a number? And so I don't have logarithms on both sides, and I can't get it so that they're logarithm on both sides because that crazy 3. It's either going to add with a logarithm, and I don't have properties that when you're adding something with a logarithm, you can do anything. Now, if you're multiplying with a logarithm, you can do something. And so I'm just kind of in the form of wanting to get it. I want to make it look like this. I want to make it look like log of some base equals an input equals an exponent. I want to get those 3 pieces. That's what I want to get. And so, and this is one input. And so I want to collapse this logarithm right here into one logarithm. That's what I want to do. And so because it's add, that means you multiply the inputs, right? Really weird property, I know. I've had students tell me before, I just had to get used to it. I had to give up on exactly why. And after a while, it becomes so natural that you're like, oh, it's just the rules of exponents. And because remember, logs are exponents. And so I'm using this property right here that if I have an addition between two logarithms with the same base, that you multiply their inputs together. And so yeah, you get really good at it. So this is going to be log base 2, and then I'm going to multiply those two together. Now it's a monomial and a binomial, so I like to write my monomial first and my binomial second, but it doesn't matter. And I'm just putting parentheses around it just so that you can see that's my input. So my input is x times x minus 2 equals 3. And then now I have made it look like this. I have a base, I have the input is x times x minus 2, and I have the exponent is 3. And so what I want to do with this, now that I've got it looking like that, is I want to write it in exponential form. And how you write something that's in log form and exponential form is I start with the base. You can start with whatever you like, but that's what I start with. And so you basically have three pieces: the base, the input, and the exponent. And you're wanting to write them base, exponent, equals input. You're wanting to reorder it, so that's how it looks, right? I start with the base, and the base is 2. Then I say, oh, I have the base, I need an exponent. And that's when I chant log is an exponent. See, log is an exponent, and the exponent is 3. And that equals x times x minus 2. And then now I've turned it into something that we were learning how to solve when we did the both tests, chapter 1 and chapter 2 test, and also, chapter 2 and chapter 3 test, and the chapter 4 and chapter 5 test. So we have been doing this since the beginning of the class. Is quadratic. That's what this is, because if I multiply this together, x times x is x squared minus 2x. And so you see it's quadratic. What do I have on this side? I have 2 raised to the third. 2 raised to the third is 8. And how do you solve a quadratic? You get 0 on one side and you factor it, or you use the quadratic formula. And I'm hoping not to use the quadratic formula. If it'll factor, I'll factor it. So I'm going to take away 8 to get 0 on one side. Use the quadratic formula if you want. It takes longer, and I'm lazy. And so I only use it when I have to. To make 8 is 2 times 4, which also subtracts to be 2. So I'm like, oh, hot diggity dog. So this is x minus 4 times x plus 2 equals 0. And when I solve that, I get x is 4 and x is negative 2. And these aren't, it's a good idea to check. These are must checks. And remember, what you're checking for is that the input and the base cannot be negative. So when x is 4, and you have to check in the original, then in here I have 4 take away 2 is 2. So when x is 4, this is looking good so far. This is log base 2 of 4 take away 2 plus log base 2 of 4, right? And this is equal to 2, and that's fine. You're allowed to be 2. And that's 4. You're fine. You're allowed to be 4. And I'm contending that this equals 3. And so we're going to try it and make sure on our calculator. So here's, this calculator's easier to see. So I'm going to use it. And on my videos, it's easier to see. Log base 2. And it doesn't matter to me if you put in 4 minus 2 or if you put in 2. It's all the same. Plus log base 2 of 4. And I'm expecting this to be 3. And it is. So I'm like, yay. So that means this is a good answer. Then the other one that I was supposed to check, I put down the answer was positive 2, but I'm sorry, the answer is negative 2. I made a mistake there. And now that I'm looking at it, I'm seeing that it's a mistake. So x equals negative 2. because I set it equal to 0, and so this should have been -2. And log base 2 of -2 minus 2. This input right here is negative, and that's not allowed. So when I put this in my calculator, -2, it's going to say error, because it's going to say, no, you can't do the negative input. That's not allowed on a logarithm. And so I have one answer, and my answer is x equals 4. So we did a good job on that. We checked it. It worked. And these are must check. You must check them for sure. And this one right here is our last one, example 9. And then there's lots of problems that you can go and practice on XYZ homework, on the textbook, or on the lab. And so you notice I got log on both sides. But because of the 4, I can't set the logs equal to one another. So unfortunately, there's just not anything I can do about that 4. That 4 is just sitting there in the way, right? So I can't equate the logarithms because I don't have just log on both sides because of the 4. And so what I'm going to have to do is I'm going to have to do like I did here, is I'm going to have to get both of the logs on the same side of the equation. And it's okay to leave the 4 on the other side, and then I'll make it look like this by collapsing it into one logarithm. So that's going to be my goal. So I'm going to leave the 4 right where it is, because the 4 is going to play the part of the exponent, is what it's going to be. And I'm going to put these two logarithms together and get the base will be 2, because they're both 2. So if you're asking, hey, what if the bases were different? What would happen then? Well, you wouldn't be able to solve it. You'd wake up and you're in a different class, knowing how to solve much harder things than what we're solving. The base has to be the same. So luckily they are the same. I'm going to have a drink of my peppermint tea. It's so delicious. And keeps my voice from cracking. So I'm going to take away log from both sides. So take away this log base 2 of x minus 3. I'm going to do the same over here. So when the dust clears, on this side, I'm going to have log base 2 of x plus 3, and then I'm going to take away log base 2, because I'm going to do that both places. I just didn't have room to write it over here, and so it was annoying me, because I didn't want to line them up. They're not like terms. So I took this away, both sides, equals 4. The reason I'm taking it away and not multiplying it or dividing it is because what was it doing with the 4? It was adding. And so I'm taking it away from the 4 so that I can get the 4 all by itself. And so now I have that property of logarithm where I have a subtraction. And do you guys remember what you do? You divide. And the one that comes with a positive log is in the numerator. So this is going to be log base 2. And then this one has a positive, so it's going to be in the numerator, x plus 3. And this has the minus, so it's going to be in the denominator, x minus 3. Oh, just all of a sudden I got a craving for one of those avocado smashes, Cafe Smitten. Logarithms will make you think of yummy food. So now I have written it in the form. I have a log, I have the base, my base is 2. I have an input, my input is a fraction, equals my exponent is 4. And what I want to do with this is I want to write it in exponential form. So now that I've made it look like this, then I can write it in exponential form, where my base raised to my exponent equals my input. And so in this case, my base is 2. My exponent is 4. 2 to the 4 is just equal to 16, my friends. Equals x plus 3 over x minus 3. And then I'm going to solve this, and they say solve normally from here. So now that I've written it in exponential form, solve normally. And so what I was first saying is, oh, this is a problem that involves a logarithm. And then I used the inverse operation of logarithm, right? I collapsed it into one logarithm and used the inverse operation of logarithm, wrote it in exponential form. And now I'm looking at it and I'm saying, oh, it's a rational. Remember, we called rational something that had a variable in the denominator. And so how we solved a rational, 2 to the 4 is 16. So I'm going to write this as 16 over 1. And I don't know if you guys remember, we crossed one way, we had other ways as well, was to cross multiply. Do you guys remember that way? So I wrote it as 16 over 1 so that I have a fraction equals a fraction. And when you cross multiply, you multiply the 16 times the x minus 3. And that you equate that with the 1 times the x plus 3. And then I'm going to put this up here because I'm just out of room. So on this side, I have 16x, I'm distributing, minus, I think 48 is 16 times 3. Let's look it up, make sure on our calculator. 16 times 3, 48, yeah. Oops, I was not showing you. 16 times 3, 48. I was checking it, making sure, right? I had a feeling it was. 1 times x is 1x, or x. 1 times 3 is 3. And now, I was saying it's logarithmic, so get the logs together, write one logarithm, turn it into exponential, right? Now it's rational, cross multiply, and now it's linear. And good news, we know how to solve linear. How you solve linear is you get the x's on one side and the numbers on the other. So I'm going to take away x from both sides. I'm going to add 48 to both sides. And when the dust clears, I have 16x minus 1x is 15x. And 48 in there. And 3 plus 48, don't make me get out my fingers, 51. But let me check it on my calculator. It's getting that time of the evening that I probably shouldn't be doing math just independent that way. And then we're going to divide by 15 to solve for x. And we're not going to say this is our answer until we check it. Check it good. And so 51 divided by 15, I think probably will reduce. They're inverses of one another, right? 51, 15, 1, 5, 5, 1. But they reduce to 17 over 5. Wouldn't it be fun if they reduced to something that was also inverses of one another? But they don't. But that would be fun. Okay, and so I'm saying, hey, is this the answer? Question mark. I don't know until I check. So it's not a good idea to check. It's not a fun idea to check. It's a must check. You got to check it, and you got to check it in the original. So this is log base 2 of 17 over 5 plus 3. And on the other side, I have 4 plus log base 2 of 17 over 5 minus 3. And my main concern is, are any of the inputs negative? Because if the input is negative, well, this is a positive plus a positive, so that's going to be positive. This is a subtraction, so it could be negative, so let's just make sure it's not. So 17 over 5 minus 3, and it's positive. Okay, so I'm thinking it's going to be good. And so we'll check it on 2 calculators. I love the dueling calculators. They're almost as fun as dueling pianos, I think. And so we have log base 2, and then we have fraction 17 over 5, and we're saying to ourselves plus 3. I'm just going ahead and allowing my calculator to do all the work, 2.67, and then 4 plus log base 2, and 17 over 5 minus 3. So I put that side in as like we saw it, 2.67. They're equivalent to one another. Neither calculator said math error, right? You can see I put in both sides, and they're equivalent to one another. And so, yep, they're equal. So that means this is a good answer. It checked. So the answer is x equals 17 over 5. Okay, good on ya. And so that's the end of this video. Oh, how do I turn it off? Right here. Stop.